all, my name is Funda Güneş. I'm a machine learning developer at SAS. Today, I would like to talk about how to explain your black box models in SAS Viya. In a healthcare study, a well-performing machine learning model is trained for predicting the risk of death from pneumonia. Based on this predicted risk, the goal was to decide which patients should be hospitalized and which ones should be treated as outpatients. Among many input variables, one variable was whether patients had a pre-existing condition, asthma or not. When interpretability techniques applied to this pre-trained machine learning model, it revealed that the trained model learned a rule, a pattern in the training data that having asthma lowers the risk of death from pneumonia. This rule sounds counterintuitive, but this was actually a true pattern in the training data. Asthma patients were more resistant to pneumonia. Because of this rule, and possibly other rules like this, the model was not put into production. After further investigating the specific rule, it found that the asthma patients actually received more intense care due to their pre-existing condition. So this was the real reason why asthma patients had lower risk of death. However, this information, receiving more intense care, was missing from the training data when the model was trained. And because of this missing information, the machine learning model incorrectly learned that asthma patients have lower risk. If the researchers didn't use interpretability and executors decide to deploy this model, the model will incorrectly predict that asthma patients are not high risk, and hence those high-risk patients would not get a chance to receive the care they needed. This example, taken from a paper by one of my favorite researchers, Rich Caruana and a few others, showed that model interpretability play an important role by helping researchers or data scientists to detect this kind of bias in the training data. Model interpretability methods in SAS Viya can help you see through black box machine learning models so you can find out important issues like this in your data and model. Let's first talk about why machine learning models are black box. Modern machine learning algorithms study training data that includes a set of input variables and labeled outputs to learn the relationship between the input variables and the output, labeled output. When we use this learned model to make predictions on new observations, in the case that where we don't know the output. When machine learning models study training data, the learning process includes many iterations over the training data, and this exhaustive learning process enables algorithms to learn very complex relationships and patterns in the data. As a result, we get a complex machine learning model. This complexity helps machine learning models to make accurate predictions on new data, assuming you had a lot of data in your training set. However, the same complexity makes it very difficult to understand the association between the inputs and outputs. Because of this, many machine learning models are seen as black box models, producing predictions without explaining why and how they are made. One example of a black box machine learning model is a simple neural network model with one or two hidden layers. Even though we can write out the equations that link every input in the model to every output, we cannot grasp the meaning of the connections simply by examining the equations. This has less to do with the shortcomings of the model and more to do with the shortcomings of human understanding. Often, the higher the predictive accuracy of a model, the harder it is to interpret its inner workings. This is where interpretability techniques come into play. Provides a lens through which you can weave these complex models. Model interpretability can meet different needs of different users, such as regulators, executives, data scientists, and domain experts. Regulators need model interpretability to make sure model makes predictions for the right reasons. For example, if an individual's loan application is rejected, the loan agency needs to confirm that this decision does not violate any laws that protect certain groups of people. Executives need some understanding of black box models so that they can logically justify the decisions they make. Lastly, data scientists, with the help of domain experts, need model interpretability for several reasons. These are to be able to detect bias that's buried in training data, similar to the first pneumonia examples that I showed, extract new knowledge that is originally hidden in the data, and debug models when they produce wrong or unexpected predictions. We can collect all model interpretability methods under two main umbrellas: inherently explainable models and post-hoc, also known as model-agnostic explanations. Inherently interpretable models incorporate interpretability directly into the model structure, and thus these are self-explanatory models. One type of commonly used inherently interpretable model is generalized linear models, also known as GLMs, which includes regular linear and logistic regression models. The regression weights of GLMs directly reflect feature contributions, hence these models can be explained through those regression weights. Assuming an efficient feature selection is performed, these models are useful for model interpretability. However, if you have complex relationships and nonlinearities in the data, these models may not be sufficient to capture this complexity, and the prediction accuracy may suffer. More recent examples of inherently interpretable models can achieve interpretability without much suffering from prediction accuracy. These models use various techniques such as regularization techniques by forcing models to use fewer features or by enabling features to have monotonic relationship with the outcome. Another popular example of inherently interpretable model is generalized additive models with pairwise interactions. For more information and references to these techniques, please see our SAS Global Forum paper, which has the same title with this talk. In this talk, I will focus on exploring post-hoc interpretability methods for explaining trained supervised machine learning models such as boosted trees, forests, and neural networks. The main idea of this post-hoc approach is to explain predictions of a machine learning model by treating the model as black box and then generating explanations without inspecting the internal model parameters. So how does it do it? Post-hoc interpretations are in general based on data perturbations. For example, they look for how the predictions change if the data is perturbed in a certain way. Post-hoc interpretability methods can be grouped into two categories: global and local interpretability. Global interpretability focuses on explaining the model for the entire population. For example, it looks for which features play an important role on the overall prediction of the model. In contrast, local interpretability provides explanations for a specific prediction of a model. Here you see a screenshot from SAS Model Studio application, which is a web-based visual interface that enables users to build predictive modeling pipelines in SAS visual data mining and machine learning. In Model Studio, model interpretability functionalities are provided as a post-training properties for all supervised learning nodes. This screenshot here shows how simple it is to request model interpretability for your pre-trained gradient boosting models. Requesting model interpretability properties does not require to retrain your machine learning model. Next, I would like to show you a case study where SAS Model Studio is used for performing post-hoc model interpretability. The data come from a FICO XML challenge, which can be found at this link shown here. And it's about home equity line applicants that are real home owners. The customers in this data have requested a credit line in the range of $5,000 to $150,000. The goal is to predict whether the applicant will repay their HELOC account within 2 years. The data has over 10,000 observations and includes a mix of 23 interval and nominal input variables. The input variables include variables such as the number of installment trades with balance, number of months since the most recent delinquency, and average number of months in file. The target variable is risk performance, which is a binary variable that takes value good or bad. The value bad indicates that a customer's payment was at least 90 days past due at some point in the 24-month period after the credit account was opened. The value good indicates that payments were made without ever being overdue. The data are balanced with around 52% bad observations. Since the focus of this presentation is on explaining model interpretability, I will skip all data pre-processing and feature generation steps. I will also skip details on how to create a Model Studio project, partition data, and assign various roles to your variables in your data. For all these details, please see our paper. Suppose you trained a well-performing gradient boosting model for the FICO data in Model Studio. In order to understand your model, you can now request global interpretability methods, variable importance, and partial dependence plots as shown in the screenshot. Let's first start with exploring the variable importance table. The variable importance table shows the ranking of the importance of features in construction of the gradient boosting model. We see that external risk estimate was the most important variable, followed by another variable called average months in file. Now that we know external risk estimate was the most important variable, let's see its partial dependence plot to further understand its effect on the model predictions. Partial dependency plots depict the relationship between a feature and the average prediction of the pre-trained model. In this figure, you can see that the predicted probability of payments being 90 days overdue decreases manually as the external risk estimate value increases. The text box to the right of the graph explains the graph by using natural language generation, NLG, in SAS Viya. All model interpretability plots have this kind of NLG text boxes they come with. And these explanations can help you understand the graph, and they are especially useful if you are not familiar with the technique. The heat map on the x-axis shows the population density at various levels of external risk, where the blue shows the less dense regions. You should be cautious in explaining this plot on the places where the population density is low. Next, let's switch gears to local interpretability. Unlike understanding the general behavior of the model, local interpretability methods focuses on explaining individual predictions of the model. For this, we need to specify individual observations that we need explanations for. If you do not specify individual observations, SAS provides explanations for 5 randomly selected rows in your data. Here you see I specify 5 rows based on the ID variable. Note that ID variable is an input variable and it must have the role key to be used here. You can assign this role through the Data tab in Model Studio. After specifying the individual observations, here I request local interpretability methods ICE, LIME, and Kernel SHAP. Now let's go through these methods one by one. Let's start with the ICE plot. Here you see the ICE plots for 5 individuals and plus the PD plot shown in blue. While the focus of PD plot was on the average effect of a feature for the entire data, ICE plots show the effect of a feature for a single observation. By examining various isolates, you can gain insight into how the same feature can have different effects for different individuals or observations in your data. We can see that the change in the model prediction for each of these individuals decreases as the external risk estimate increases, which matches the behavior that we had seen in partial dependence curve. Each observation is affected by external risk estimate slightly differently. For observation 152, there is a steep decline in the model's predicted probability of late payment when the external risk estimate is between 60 and 70. Whereas for observation 5429, the decline is more gradual between 60 and 70, and it's steeper after 70. Next, let's explore line explanation of a false positive prediction. This instance was predicted as a high-risk HELOC application with a predicted probability of around 0.97. In line, the main assumption is that machine learning predictions in a neighborhood of a particular instance can be approximated by a white box interpretable model such as a regularized linear regression model like LASSO. This local model does not have to work well globally, but it must approximate the behavior of the pre-trained model in a small local region around that particular observation of interest. On the left, you see the regression weights of this white box model that are used to explain the prediction of the pre-trained model. And the feature values of this instance are shown in the table on the right. We see that for this instance, there are only two variables that are on the left side of the plot, decreasing the risk of default, whereas all other predictors increase the risk of default. Next, let's explore a kernel SHAP explanation for a false positive prediction. The truth for this instance is good, but the model predicts it as bad with a high probability around 0.9. Different from Lime coefficients, kernel SHAP explanations for feature contributions do not directly come from a local regression model where the features join the model only in a certain order. The SHAP explanations take into account features can join the model in any order, so order doesn't matter. Hence, they are shown to be more reliable explanations when compared to Lime explanations. Even though the model has such high confidence in its predictions for this instance, which was probability around 0.9, we don't see the same confidence in SHAP explanation because the top 5 Shapley values almost equally weighted to the right and left side of the plot. This explanation can be used as a warning sign for a false prediction and can be useful when debugging the model. In case study 1, we talked about how to request model interpretability in Model Studio application of SAS Viya. In Model Studio, we run cloud analytic services or CAS actions behind the scenes to perform model interpretability. If you prefer to use a programmatic interface, you can call all those actions by yourself in a SAS session through the CAS procedure or through Python or R through the SWAT library, or you can use REST APIs. Here's a simple code snippet that shows how you can perform model interpretability by using CAS actions. You first need to train your machine learning model by your preferred algorithm. Here I trained the forest model and saved the score code in a SAS analytic store called forest model. In the second box, I used the score code to request Lime explanations for some observations specified by the query variable. If you're interested in learning more about SAS Viya programmatic interface, please see the second case study in our paper. This example uses CAS actions through PostCAS to perform model interpretability. The whole code is available at our GitHub repository that's shown on this slide. In summary, we talked about model-agnostic, global, and local model interpretability techniques through a case study in SAS visual data mining and machine learning. I hope you can use those valuable techniques in your projects to explain, validate, and debug your black box machine learning models. Here are some additional information and resources to learn more about model interpretability in SAS Viya. Thanks for taking time to listen to my talk. For more details, be sure to check our paper. Also, feel free to reach out to me through my email if you have any questions. Thanks again for listening to me.